Okay, so when we say it's a rate, that always means it has to be divided by time. Okay, so the rate at which work is done, how quickly we are transforming energy, how quickly we are applying a force which covers a displacement, that's what work is, right? Work can be change in energy or force times displacement. So the unit for work, or the unit for power is watt. Where do we see watts most often? In light bulb, right? Lights, right? It's our transformation of energy. So a watt is equal to a joule per second, which means work has to be in joules like usual, and time has to be in what? Seconds. Has to be in seconds. So most of the case, that's the, or most of the time that's the case, and that it's already given to us in seconds, but that's something to think about, is that your time has to be in seconds in order to solve for power. Okay? We can also measure power in horsepower, which where do we see that the most often? Right, in vehicles or in engines. Okay, so engines. So we're going to measure horsepower, and horsepower is 746 watts. So it's a much bigger unit for power. Day-to-day things are not measured in horsepower because it's such a large unit for power. Okay, so that's a conversion that you'll need to know. Okay, so you might want to star that or highlight it or something, but that's one that you'll need to know and use. Okay, so here's our equation that could go on your equation sheet. Power is equal to work over time, or you can think about it in terms of energy transformed over time. This bar above here just means average power, right? There could be instantaneous power, which might change, depending on how quickly you have your foot on the gas or whatever it is. But we're always going to talk about average power. So if we lifted something and it took this much work and we did it in 10 seconds, that doesn't mean we necessarily lifted it at the same rate the whole time. But the average over that whole time would give us our average power. Okay, so the very simplistic equation you need for power is work over time. Okay? Okay, power and energy are not the same thing. Right? Power and energy are not the same thing. Okay, the amount of work that we have the ability to do, or the amount of energy we have the ability to transform as a person, right, as a human person, is very limited. Okay, what are some things that might limit the amount of work that we can do? So our limitations are the fact that we can't expend energy constantly, right, and we can't do it for infinite amount of time, right? So we could sprint up 2 flights of stairs. It would take less time, but it takes more energy, right? We could walk up the same flight of stairs, which would take more time, but maybe less energy, right? So power is more about the rate at which we get that done, right? We're doing the same amount of work because we're climbing the same height. We weigh the same thing the whole time, right? We're expending the same amount of work, but the rate at which we do it can depend or can change the amount of power we are outputting. Okay, does that kind of make sense? Okay. All right, so let's try this one. A 70-kilogram jogger runs up a flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. What's your output of power? Okay, so as we're running up the stairs, right, what are we gaining? Right, let's just think from bottom of the stairs to top of stairs. What have we gained? Height, okay. If we know power is equal to work over time, and we know work is equal to a change in energy of some kind, what type of energy have we gained from the bottom of the steps to the top of the steps? We've gained potential energy, which means a change in energy could be mg, right? We've gained potential energy on our trip up the stairs. So that's the equation we would use for work, and we have our time. Okay, so any equation for work could go here in the numerator of this equation, right? But as we're moving, we're gaining potential energy, right? From the bottom to the top, we've gained potential energy. At the bottom of the stairs, we're not moving, and at the top of the stairs, we're not moving, right? So we're looking at a change in potential energy there. Okay, or you can think of it as another way. As we climb the steps, we are overcoming gravity, right? We're overcoming this gravitational pull, right? So you could also think about it as force times displacement, where this would be the force of gravity. This would be the displacement that we travel. So you can think about it in whatever way works best for you, but I like to think about it as a change in potential energy. In which case we would say 70 kilograms times gravity, which is 9.8, times the height over the 4 seconds it took to get it done. Okay. Go ahead and grab your calculator if you don't have that yet. All right. Tell me what we had for our final answer there. 771 point what?
8.
Okay, good. And what's our units here? Watts. Yeah. Okay, so if we put that into horsepower, what are we looking at here?
1 point something.
Right, a little over 1 horsepower. Okay. All right, very good. If I asked just for the amount of energy it took to do this task, not the power, if I just asked for the amount of energy, what would we be doing? Yes, solving for just the transformation of energy. So all I would do is basically, if I know that I overcame or I gained potential energy, right, that's all I have to do is use the numerator of that problem. I eliminate the time aspect of it. So I'd go 70 times 9.8 times 4.5. Right? Or I could just multiply that by 4 seconds since we had just solved it. Okay? But the energy required, right, I transformed this much energy to get up the stairs in 4 seconds. Okay, and so that comes out to be what? 2,800, 3,100 or something? I don't know. 30 something? 38.
3087.
Oh, 30. 3,087. And what's our units for energy? Joules. Good, joules. Okay. So remember, power is the rate at which the energy gets transformed. All right, a cliff is a 122-meter vertical climb. The record time of 4 minutes, 25 seconds was achieved by a 65-kilogram man. What was his average output during the climb? Okay, so what sticks out to you here?
4 minutes.
The minutes, right? So get that converted all to seconds, and then go ahead and solve yourself. Okay, what did we end up with?
293.26 watts.
Yeah? Okay. So a much less power output here, right? The power output was much less, but do you think they had to expend a lot more energy than the person before?
Yes.
Yeah, right. The energy expended was greater, but it took more time to do it, right? We don't really care about the path it took him to get up the mountain, right? He could have sprinted the first 120 meters and then stopped and then waited and then went the last 2 meters. You know what I'm saying? We don't care about the path it took him to get there. This was his average power output the whole time. So it doesn't mean that he climbed steadily at that power output or at that rate, but that was his overall average, right? Some parts of the climb were probably easier than others, things like that. But he might have had to work a lot harder, but his power output was less than the guy that just ran up 1 flight of stairs, right? All right. Now we're going to look at power behind cars or moving objects, okay? Cars do work to overcome friction, to overcome gravity, to overcome all these types of things to get into motion, right? They overcome friction, they overcome slopes, which would be overcoming, gravity, all that kind of stuff. But they have limitations too. So we have physical limitations as humans in terms of our biological systems. Cars have individual horsepower ratings within their engines that limit their work or their power output as well. Okay. Oops, sorry. Okay, this is our equation that we're going to look at for work over time. And now with cars specifically, we're kind of looking at this version of work. And what is this work? A change in what? Kinetic energy, right? Usually cars aren't lifted in the air, right? Usually they move forward or backward, so they have a velocity change that would equate to their change in energy or their power output. So when we say work, we realistically need to be thinking a change in kinetic energy. So we don't want to forget that this equation could also be final kinetic energy minus initial kinetic energy. Okay, so think about it in terms of Work still needs to equal delta KE, not just necessarily 1/2 mv squared, right? If our initial starting is 0, then that's going to make our problem a lot easier, but you could have a delta there as well. Okay, yeah?
So if you're like trying to find the power for somebody who's moving like just forward, you would use kinetic.
That's right.
Okay.
That's right.
But then if you were doing like
All right, so a 1,000-kilogram car accelerates from rest to a velocity of 15 in 4 seconds. Calculate the power output of the car. Right now, we're going to ignore any frictional forces that act on the car. We're just going to look at what its true power output would be. So power is equal to work over time, which is also equal to change in kinetic energy over time. Okay, so when it says it accelerates from rest, what does that help us with?
Initial 0.
Right, our initial kinetic energy. So if we say final kinetic energy, 1/2 mv squared, minus initial kinetic energy is 0 over time. Okay, so that's going to be equal to power. Yeah, I think it's going to ask us for that pretty soon. If I'm guessing right. Okay, so in watts, what did we get?
28,125.
Okay. And then if we want to convert to horsepower, which is usually what we'll do for vehicles or engines of some kind.
37.7.
Okay, we'll divide that by horsepower. I'm sorry, yeah, divide that by our conversion factor to get to horsepower. And we get what?
37.7.
37.7. So not a real high-powered vehicle here. Right?
what is usual horsepower?
I'm not going to... So just kind of see what we're looking at here. Power is equal to work over time. Work is equal to force times displacement over time. Right? Are we with me so far?
Yeah.
So what does displacement over time equal? Velocity. So power can also be equal to force times velocity. This is another version of our power equation that we can use.
Interesting.
Or set up our system. Right, we've got a 10-degree incline. My frictional force, I drew it the wrong way. Remember, our car's going up the hill, so does that make sense why our frictional force has to go down? All right, I drew that the wrong way. So parallel plus friction minus applied, right? The applied force is what's getting that car up the hill. All right, there we go. That makes much more sense now. Okay, so this net force has to be what if we want our car to move at constant speed? The net force has to be what if we want to move at constant speed? 0. Okay, so our parallel is 2382.45. Our friction is 700. So our applied force has to be equal to the combination of those, right? So that means our applied force is what? 3082.45, right? And so we'll take that multiplied by our velocity to find power. So power equals 3082.45 times our velocity. What's the problem with our velocity here? We got to change it, right? It's got to go from kilometers per hour to meters per second. So times 0.2778. Right, that's our shortcut. And I think that comes out about 22 meters per second. Okay. Which means our power output is, give me a better number here. I have a rounded number. That 60,430.4? 68,000. Okay, sorry. My bad. Okay. So now if I want to put that in horsepower, what am I doing?
Divide by 746.
Yeah, divide by 746. And I get horsepower around 91, 92-ish. Okay, good. It's not a trick. Okay, they use 140 newtons to push a block at constant velocity of 2.2 meters per second. What is their power output? Doesn't say anything about friction here.
308.
Yeah, 308 watts. That's the limit. Force times velocity. That's it.
It's a toughie.
Right?
That should be on the test. I made great.
You think?
Good old number 10.